I'll start recording. Hi, everybody. Happy Tuesday of the last week of classes. Thanks for being here. A lot of announcements today, some logistical stuff. Homework 2 grades have been posted, and I think I got through all of the backlog. So everything except for lab 9 has been graded, I believe. If there's something that hasn't been graded that you're expecting to change, send me an email, let me know, because chances are I'm not aware of it. So make sure that you check your Canvas grade and make sure that it aligns with what you expect. So I'll show you something. So I have some more things to grade, but if I view it as a student, I've put in, this is a test student, so I've put in some grades for random assignments. And so if I go over here to the grades, you'll see like most of these are missing. That's just because I don't grade the test student, and the test student also doesn't submit anything. But the thing is up here, so currently the test student is not doing great, but this total and the letter grade, that's except for lab 9 and the final exam, that's what gets submitted to to Gale Express. That's the letter is going to go on your transcript. So if you look at your grade right now, and that's something that you think is not accurate to the assessments you've received, then send me an email. So ball's in your court. I think I've done everything except for lab 9 and the person who submitted homework 2 between this morning and now. So make sure that that is aligns with your expectations. Yeah.
So like, I see like the final exam is like on there, and if we're just like wanting to calculate our grade, right? And we put like, say you put like 50 out of 100 on there, and I can calculate the total grade, is that like a reflection of what your grade would be if you got a 50 on the final? And
Yeah, so that would be this, I think. Yeah, so then if you go back up here, and then it's like this is if you can play around with what you think you get on the final. And that shows you the
well, yeah, I'm just.
projected score. Yeah. Yeah. Any other questions?
Final next week?
Final is next week. It is Thursday at, please hold. I believe it's at 1 o'clock. Thursday, 1 to 3. 1 to 3 p.m. Next Thursday. No meeting on Tuesday. Just Thursday. Okay. So that's my thing about grades. So yeah, so the grade that's on Canvas should roughly translate to what you expect. So if you need to resubmit something, then resubmit it as soon as possible, because where is it? I'm not gonna accept late work past Friday at 11:59 p.m. Okay. Hold on. Let me go through top down. For homework 2, if you didn't submit, I either left a comment or I emailed you. So make sure to do that as soon as possible. Tech Club is meeting tomorrow. It's going to be like a study hall type event where you just show up and bring your homework or bring your study guide and work on that. Galileo 114, 5 to 7 p.m. If you do want to come, if you want pizza, you should RSVP for pizza so that I know how much to buy. The link is in today's active learning. It's tomorrow, 5 to 7 p.m. And this is for like all CS, data science, tech majors and minors. So just fill out the form if you want to come, so I know how much pizza to buy. Okay, so no late work is gonna be accepted past Friday. So get it done. If for some reason that you will not get anything done, or everything done by then, you have to talk to me. Question.
Yeah, so, no, I think I missed like one or two classes total, but I think I missed like so many active learnings, I don't know what's going on. Did you
Come
guys-
talk to me afterwards.
We can fix that up.
Talk to me afterwards. Yeah, so if you're not gonna get everything done by then, you have to talk to me. Incomplete is a possibility. What happens with incompletes is you get 37 days after the grades are due to get everything done, and the grades are due on the 22nd of December. And so that would give you until Tuesday, January 28th, as like the hard deadline to finish everything up. So most of you this doesn't apply to, but in case it does, I wanted to make you aware of that. If you are interested in the summer research program, I wanted to tell you about this. So if you've ever walked down Galileo and you see those posters, there's probably also some in Brousseau, but I don't really go in Brousseau very often. But there's posters on the wall of here's research that students have done. Those are typically done during the summer research program, where you are working with a faculty member and you're working on a project, and then you can write up a paper or make a cool poster and then say, hey, look, I did this research. And that's also good for job applications, or if you want to go to grad school or something like that. So if you're interested in that, there's an info session on Friday at 1:30. There's a Zoom link. I can forward you this email, the information if you're interested. I recommend it. I think it's a good experience. My last announcement is course evaluations. If you get annoying emails, if you do the course evaluations, chances are they will not email you anymore. And you also probably won't get a pop-up in Canvas every time you do it. Question? I'm pondering if we get to like 80 or 90%, then I give everybody extra credit.
Yeah, really?
Maybe not that much. Yeah, I'll give you guys extra credit if we reach a certain threshold. So I'm gonna provide, depending on how today goes, if we have a lot of time today, then the class can just be evaluation time. Otherwise we'll have time on Thursday as well. So do them. Also, course evaluations are really helpful for instructors, because we'll go through the whole semester and I'm like, get some feedback from you guys, but I'm also kind of wondering, like, on a whole, how is the course going? What could I do to improve? What did I do well that enhanced your learning? So it's good from my perspective as well to see how am I doing? And also helps us to improve for future versions of this course. So course evaluations, very useful. We greatly appreciate them. I'll give you some extra credit, probably. All right, so for today, we are going to learn about binary search trees. So I'm going to pause the recording for a second. I'm going to split you in pairs probably. You'll move around and then we'll go into the lecture bit, and then I've given most of you a worksheet and then we'll do that. Okay. Pause recording. All right. Let's talk about binary search trees. Okay, so this, as a reminder, this part is not on the final, but it's also useful to know, especially if you go on to take algorithms. So that's where we're at. So binary search tree is an abstract data type. We've kind of talked about what these are before. We've made several abstract data types ourselves. An abstract data type is a data type that we make up in order to serve some purpose. So in some application or program, we use this data type And that data type has public functions and so public things that like the outside users will use. It also has some private functions, which are just like internal and not meant to be used externally. So that's like the copy over method from LL. That's something that we don't necessarily want the outside user to say ll.copyover. That's just something that we want to use internally. And then these functions are supported by some kind of data structure. So either an array or a linked list or something else. So we've made like a linked list, that's an abstract data structure. We've made stacks and queues, those are also abstract data types. So let's talk about a new data type. It's a graph. If you're enrolled in, I can never remember the number, 485 next semester, graphs and applications, that will be, this is what we're going to talk about in that class. There's also still room if you want to join the class. So a graph is defined by two sets. One of the sets is called the vertices or the nodes. And so those are like, we draw dots to represent each vertex. We can call it a vertex or a node kind of interchangeably. And then there's an edge between them. So we draw a line between two dots to say this is an edge between one node and another. So this up here, this is a graph. We represent a graph as written with G equals V comma E, where V is the set of vertices and E is the set of edges, where we basically pair two things together. So this is an example of a graph where we've got vertices 1, 2, 3, and 4, and we've got edges 1 and 2, 2 and 3, 3 and 4, 4 and 1. And so we can draw that. So like if I label this one 1, and then there's an edge between 1 and 2, let me draw the rest of these, 3 and 4. So 1 and 2, we've got that edge. 2 and 3, we draw a line between them. 3 and 4, and then 4 and 1. So we make a square. This is a graph. It's an abstract representation of something. In real life, we could say that these dots represent something. But at the graph level, we're just like, we're taking that up one level. So one of the possibilities is maybe this is like, I don't know, like a friendship diagram. Like person 1 is friends with person 2, person 1 is also friends with person 4, and then 2 and 4 are friends with person 3. So it can be used to represent relationships for just about anything. You just have to decide, here's what that relationship means. Here's what the individuals are, so the vertices, and then here's the relationship between them. So a graph can be used to represent all sorts of fun things. So to get to binary search trees, first we have to talk about what a tree is. So these two graphs, so this guy and this guy, they have what we call cycles. So where like we can start at 1, we can go around to 2, 3, and 4, and we end up back at 1. That's a cycle. This one also has a cycle. It has 2 cycles, 1, 2, and 5, and then 2, 3, 4, 5, and we go back to 2. So a tree is just a graph that doesn't have cycles. So like this graph here, if we start here and we go down 1, there's no way to get back up, back to our original node. So a tree is a graph without cycles. So there's nothing like that. That's not allowed. Note that a tree is also a graph. It's just a graph that doesn't have cycles. Okay, so once we have a tree, we can orient it to serve our purposes. So if this, I'll move this guy down here. So if this is a tree, that's all fine and dandy, but we can put it in, we can draw it a certain way to suit our needs. So the first thing we do is we need a root. We pick one node and we call it a root. So like We could pick 4. Maybe that's the root. And then we can redraw it. So if we have 4, and then we say the root's at the top, and then all these, we can think of the lines as like branches, and we draw them going downwards. So 4 goes to 5 and 6. 4 also goes to 1, 2, and 3. Okay, so the branches go down and out with the root at the top. That's how we draw trees in this context. And so we assign this orientation some meaning. So the node that's above another, we call that the parent. The node that's below, we call that the child. So like 4 and 3, 4 is the parent, 3 is the child. 4 is the parent, 2 is the child, 1 is the child. 5 is the child of 4, but also 5 is the parent of 6. Is that terminology making sense? So we assign it meaning based on where it is vertically. So these we can call a branch. We also call the endpoints, we call those leaves, because computer scientists like to name things. And so since we're working with a tree, the endpoints of a tree are its leaves. And so like 6 is a leaf, so is 1, 2, and 3, but 5 and 4 are not leaves. Okay, so 4 is the root. The orientation doesn't really matter, just be consistent. So if we decided to draw it like 4 on the left or 4 on the bottom, just be consistent and like work your way up or work your way sideways instead. Okay, so once we have a tree, we need to make it a binary tree. So we're going to add a definition that affects the kind of tree that we're going to get. So binary means 2. And so what that means for our context is that every parent is going to have at most 2 children. So could have 0, could have 1, could have 2, cannot have 3. And so that's a binary tree. So this is a binary tree. It also happens to be a binary search tree because we're going to add a definition in order to get to a binary search tree. And so the way that we get to a binary search tree is we build it in a special way. So the way we're going to do it is we're going to insert items into our tree in a special way where we start at the top. So like in this tree, we start at 25. And then the main rule for a binary search tree is everything that's less than this node, 25, is going to go to the left of 25. We're going to go down to the left and keep searching. If it's greater than 25, we go down to the right and keep searching. So you'll see like 20, that's less than 25. 36 is greater than 25. So that's how we build this structure. Yeah. Yeah, it's kind of like, so like quicksort partitioning, kind of. Yeah, where, yeah, we'll have something roughly in the middle, and then we'll go left or right, depending on where it belongs. Yeah.
So a child is a leaf.
Maybe, not necessarily. Like 20 is a child, but it is not a leaf. Yeah, so 20 is a node. So 20 is a parent and a child. The leaves are 5, 12, 22, 28, 38, 48. Yeah, 48. So a leaf is something that doesn't have a child. Like it ends here. Any other questions? Okay. So the way that we build it is, let's say we've got some new value X that we're going to insert into this tree. So we start at the root. If there's no root, then we did it. and this is now the root. So let's say we're gonna have 3, 2, 4, 1, 5. Let's say we're gonna insert these things into a binary search tree in that order. So for 3, there's currently no root because we don't have a tree. So 3 is going to be the new root. Hooray. So 3 is added. And then we look at 2. So we start at the root. There is something. So we go on to step 2. So we compare 2 to the root. We compare 2 to 3. Where does it fall? Less than. So we go to the left. So currently 3 doesn't have any children. And so we place 2 as the left child. And then we look at 4. 4 is greater than 3, so we go to the right. There's currently no child there, so we put it there. 1, we compare 1 to 3 and go left. We compare 1 to 2 and go left. And then put it there. For 5, we compare 3 to 5 and go right. 4 to 5 and go right. And we put it there. So yeah, so that's the basic process, is we go left or right depending on whether it's greater than or less than. So I would like you to turn to your partner and kind of brainstorm for a second. What do we do if we have something that's equal?
Thank you.
All right, what do we think? Might have to make a new tree, maybe. Maybe. What do other people think? Keep it the same, do nothing, move on.
Yeah.
That's also an option. Yeah. So maybe we don't want to allow duplicates in our tree. Any other ideas?
Maybe you replace it.
Replace it? I mean, you could. That's basically the same thing as just doing nothing. But yeah, cool. Fun thought experiment. Okay, so we're gonna draw the first one on the worksheet together. So yeah, so get out your favorite writing utensil. Okay, so to create this binary search tree, yeah, question. Sure. The examples, all the examples I've given you do not have any duplicates.
Right, but if there was a video, what would you do?
Yeah, you just asked us what would you do and then you decided to give us an example. You didn't give us
I mean-
an answer.
So
What if I'm in a situation where there is a duplicate?
then you as the programmer need to make a decision.
What's the generally accepted answer?
Probably no duplicates. Probably just ignore it. But it depends on your situation.
So on the final, what are we gonna say?
Binary search tree isn't on the final.
Oh, cool.
What's on the final? There's a study guide posted to Canvas, and also if we have,
Right? So I was logging on the Canvas, all of things is great, thanks to Microsoft.
okay, all right, let's create this binary search tree. So we start with 71. 71 to the root, hooray. We look at 32. 32 is less than 71. So we put it to the left. Now we look at 94. 94 is greater than 71.
Right.
Great job. All right, 84 goes to the right of 71,
It goes to the left of 94.
left of 94. All right, 17 goes to the left of 71, left of 32. All right, 49, less than 71, greater than 32. All right, 85, greater than 71, less than 94, greater than 84. 53, less than 71, greater than 32, greater than 49. 42, we go left, right, left. And then 96, greater than 71, greater than 94. Cool. So you can see we have like levels here. So I didn't draw it especially nicely, but we've got like level 1, level 2 with 32 and 94, level 3, and level 4. There are other data structures where you can make it so that everything is very evenly balanced. But we're just looking at binary search trees just for today. So there's other ways you can take this where you'll notice like there's a hole here, there's a hole here. There's other data structures where we can kind of fill in those gaps. But we're just dealing with binary search trees today. Okay, everybody drew their tree? Cool. This is what you'll do for the rest of them. We'll get to that in a minute. I'm gonna finish talking through the things and then we'll do that. Okay, so to search for a tree, so search through a tree. So let's say we're looking for, what did I say, 49? So let's say I want to look for 49 in this tree. The process is basically the same thing as inserting, except I don't actually do anything. I'm just looking for it, right? So if I'm looking for 49, I start at 71 and I ask, is the thing I'm looking for greater than or less than the node that I'm currently at? If it's less, then I go to the left, what we call a subtree, like this whole thing. That whole thing is a subtree, the left subtree and the right subtree. And then we repeat the process. So this is a recursive data structure that we can go through. So we go 71 and then we go left. And then when we're looking for 49, we'll go right at 32 and then we find it here. Hooray. If we wanted to find 48, we go through the same process, right? So we start at 71, we go left. So let's say we're looking for 48. And we find 49. 48 is less than 49, so we go right. We find 42. And then 48 is greater than 42, so we would try to go left, try to go right. But there's nothing there. So in that case, we would say we did not find 48.
Why are we doing this?
Because we have this data structure where we've stored these things in this way. And so a natural question is something in this structure? Do I have this in here yet? So because a tree is not a list, like we can implement it as a list, but it's a different kind of structure. So yeah, so the tree gives us this information of less than and greater than. We've assigned it this structure. And it's not a linear structure. So graphs can give us a structure that's non-linear, which because not every data that you're going to use is going to be linear, right? You're not always going to have just a sequence of things. You're going to have sometimes some complex relationships that you want to model in some way, and then a graph is a really good way to handle that. So when you have this nonlinear structure, one of those types of structures is tree. So when we're using a linear structure like a list or an array, we iterate through it. Like we start at the beginning and go to each thing until we find what we're looking for. When we're working with this nonlinear structure, we do traversal, which is where we go through this the structure in an orderly manner. And there's a lot of traversal algorithms. One of which, so we'll look at 3 today, which is pre-order, in order, and post order, which is where we start at one thing and go around the structure in the same way, and we just choose to print when we found it in a certain order. There's also other algorithms that we can go through. There's like breadth first search and depth first search and others as well. So if you take algorithms, we'll go over these. But these 3 are the ones that we'll look at today. So yeah, so traversal is how we find out here's what's in the structure. So the idea for at least these 3 that we're going to look at today is, do you remember from like elementary school when you have like the turkey drawing and you'll trace your hand, and then you'll like draw a turkey on your thumb or something? That's kind of what we're going to do for the tree. So this is a drawing someone made on the internet where we've got this binary search tree, or this tree, and we start at the root and we go left and we draw our way around. So kind of tracing it like the hand diagram. And we decide when we're going to record each node that we come across. And we've got 3 options. So one option is to record it on the left-hand side. So that's the blue option. So on the left-hand side, that's what we call pre-order. If we record it when we reach the bottom of a node, then that's what we call in order. So that's the green one. So as we go around and we say, okay, so like as we do this tree, the first thing we get via in order traversal is H. So that's the first time we reach the bottom of a node. So we would do H, and then A, and then C, and then D. Whereas if we did pre-order, we record E first, and then D, and then A, and so on. So we're doing the hand turkey tracing, but it depends on when we're recording that item. And then post order is just when we reach the right side of it. So like for E, would be the last thing we write down on if we're doing post order. So we'll only get to the right of E the very last time. Okay, so something to ponder that I would like you to talk about. So first off, the BST property, binary search tree, it holds if everything to a left of the node is smaller than that node, and everything to the right of that node is larger. And only if that holds for every single node in the tree. Okay? So the question is then, how do we delete something? So talk to your partner. Try and figure out, maybe work with the example that we've done so far and figure out how do we delete something and still have this property hold. Go for it.
Yeah. Yeah, and then like a photo from the third last room. I was like something.
Yeah.
And then we have to deal with this to look at the less than that. Saves less. Less than that. Which one says the right?
So everything.
I think you're right. I think you're right. You were right. What's greater than? Once we ask all. Yeah, that's what sounds the parents who go sit and watch that much. So that's just like
All right, what are we thinking? How do we delete something? How do we, so, let me draw that again. Okay, so let's say, I don't know, let's say we want to delete 49. So we want to remove 49, but we want to keep everything else. Yeah.
So for 49, 50 groups are supposed to move that out to where 49 is.
Yeah.
You could go back through for the value, each child to the left, like anything under it, like fine.
Yeah, that's the basic idea. So you go right one step and then you go all the way left. Because the idea is you want to find what's the next thing bigger than this. And then you replace that. Yeah, and so it gets a little tricky when, let's say we want to replace like the whole root. Let's say we want to delete 71. The reasonable, if we follow this, we go right and then we go all the way left. That gives us 84, which is the next bigger thing from 71. 84 has a child though. So in like the hand wavy way to explain this, 84 would become the new root, and then we have to adjust this relationship 84 and 85. So 85 ends up being where 84 used to be. So yeah, so we won't go too much into detail, just a practice of thinking, how do we do this and make sure that this property still holds? Okay, that's all the lecture that I have for you. So the rest of time, do the worksheet. So for the worksheet, we have so I've got lines of numbers for you. And so first build the tree. And then write what are the pre-order, the in-order, and post-order traversals. I'll throw that slide back on up. Try to find a node. Try and find something that's not in there and convince yourself that it's not there. And then try to delete a node and figure out if you did it correctly. So just some examples. Once you finish all of this, do the course evaluations and then check in with me. We'll see how much time we have left. All right, go for it. I'll put this back up.